We have learned how to use the Fresnel equation or the wave equation to find out the solutions of the EM plane wave in an isotropic medium. These EM plane wave, we call them normal modes or eigenmodes. And now I will show you the orthogonality of these normal modes. That is, these normal modes, they will be perpendicular to each other. We start with the Maxwell equation. Divergence D is 0. For EM plane wave, the gradient operator can be replaced by minus jk, where k can be written as the amplitude k times s hat. S hat here stands for the unit vector along the k direction. Besides, the amplitude k can also be expressed as n times k0, where n is the effective material index experienced by the EM plane wave. And as we know, in an isotropic medium, for specified direction, we can find out two solutions, right? So, for this equation, we can rewrite it as hat dot the first solution d1 is 0. Besides, s hat dot d2, the second solution is also 0. So, we can say that the s hat, the direction of k, the direction of the wave, is perpendicular to d1, and it is also perpendicular to d2. Okay? Then we use the curl H. We know that curl H is j omega d. So again, replace the gradient operator by minus jk. You will have minus jk cos h is j omega d. As a result, we can express the d field in this way. Minus k cos h over omega. Okay? Besides, from another curl equation of Maxwell equation, you will know that k cos E will be omega mu sub 0 h. By using this equation, we can replace h by k cos E over omega mu 0. So h here will be replaced by this equation. So we can rewrite d field in this way. Minus k cos E over omega square mu sub 0. Okay? And k here can be written in this way. So we take this expression back into this operation. Then you will have minus k square over omega square mu 0 times s hat cos E. Okay? The next step is to expand this expression. We have two curls here, and we can use the back cap rule to help us to obtain that the d field is minus n square over c square mu 0. We have replaced k in some expression. Please try to do this by yourself. And inside here, we use the back cap rule to have s hat times s hat dot E minus E times S hat dot S hat. Okay? Then we take the minus sign into here. You will have n squared over c squared mu sub 0. And inside here, we first deal with this one. After we taking the minus sign into here, this term will become positive. We have E field first. And as we know, S hat is the unit vector along k direction. So S hat dot S hat will give you the square of the S hat. Since it is the unit vector, so the square of S hat is just 1. And minus S hat times S hat dot E. This is the final expression for the D field here. And now I would like to show you that from this expression, you can see the relationship of D, of K, and the E in space. First of all, we consider that there is a K vector here. Okay? Suppose we have a K vector here, and according to our definition, along this direction we have a normal vector S hat. Unit vector S hat, sorry. S hat is the unit vector, and then if we define, there will be a E field like this. If we have the E field like this, and clearly the E field can be regarded as consist of two components. One component is what? Is parallel to the k direction, and the other component is perpendicular to the k direction. Okay, so here is E parallel, and here is E perpendicular to the k. Suppose that. And for this one, for the component of E which is parallel to k, can be expressed as what? Let us see. Here, S dot E means that the projection of E in S direction. So, according to this plot, S dot E means the magnitude of this distance. The projection of E in S direction means the magnitude of this distance. And S hat is the direction of this, is the unit vector of this direction. So combine of this. The whole expression here represents the component of E in S hat direction, which is defined as E parallel in this plot. Okay, so S dot E gives us the projection of E in S hat direction, and S hat gives this magnitude a direction. So the whole expression here just means the E parallel. That is the component of E which is parallel to K or parallel to S hat. And I have said that the E field have two components. One is parallel to K, the other is normal to K, right? As a result, the total E minus the E parallel. So what will be left? As the total E, I shall use another color. The total E, too dark. Maybe this one. The total E minus the E parallel component. So this one represents the component of E which is normal. I shall write in English. The component of E which is normal to S hat or K vector. Okay? So the here just means this component. Okay? That is E normal. And from this expression, you will know that the D field is in proportion to the E normal. Okay? This means that the D field just in this direction. Because according to this expression, the D field is a factor times the E normal. So the D field is in this direction. So we plot D field in this color. So the D field is like this, parallel to E normal. So from this plot, you can clearly have a conclusion like the E field, the D field, and the K vector. These three vectors, they are in the same plane. Okay? So if we explain this expression by this figure, you will see that the blue one is the K vector, and the orange one, maybe it's orange or not, and this one is the E field. And if you know the K vector, if you know the E field, then you can obtain the D field. And these three vectors, they are in the same plane of the gray. For the plane in gray, the D, E, K, they lie in the same plane like this. Okay? Try to think it again. So, from the expression, we know that the D will be in proportional to E normal. Besides, I would like to remind you that according to divergence B is 0, we can also have K dot B and K dot H. Both of these two is 0. Besides, we also know that the E is normal to H, and the D is also normal to H. As a result, we can say that the Poynting vector P, which is defined as E cross H, and now this one will be not parallel to the K vector now. Okay, so we can explain this result this very important result in an isotropic medium by this figure. As I have said, we have K here, we have E field, then we can know we have the D field now at this direction. And according to these two conditions, we know that the H field and the B field, these two vectors should be normal to E and D, and also should be normal to K. Since these three vectors they lie in the gray plane, so H and B vector they should be normal to the plane in gray, like this figure. So the purple one here is the vectors of H and B, and according to the pointing vector, E close H. Use your right hand to find out the direction of P. The E close H will be the vector in green shown here, and clearly the P direction is not the same as the K vector. So in an isotropic medium, the pointing vector P is not always parallel to K. Okay, this means that the direction of the power may not be the direction of the wave. K here is the direction of the wave. P is the direction of the power. So, as we know in isotropic medium, in simple medium, in isotropic medium, we always know that the power direction is the same as the wave direction. But however, remember that in an isotropic medium, the power direction may not be the same as the direction of the wave. Okay, after we have obtained the expression of the D field in an isotropic medium, now I would like to prove the orthogonality of these eigenmodes by using the equation derived from the wave equation. K close E plus omega square mu epsilon 0 epsilon tensor here times E is 0. Here we put epsilon 0 here, so we have to put another epsilon 0 here. And as we know, the K vector can be expressed as the amplitude of K times the unit vector S hat. So the above equation, by taking this expression into this equation, we can have K squared times S hat minus I times E minus K0 squared times epsilon tensor over epsilon 0 times E is 0. The I here is the unit matrix. Okay, so as we know, if we know the material properties of an isotropic medium, and we also know the direction of the wave. So for the same material properties and the specified direction, by solving the above equation, we can have two solutions. That is, we have one solution which experiences the material index N1. So this solution will correspond to a K vector K1 and the E field E1. For another solution which will experience the material of N2, and it has the corresponding K vector K2 and the E field E2. These two are the solutions to this equation. So if you take these two into this equation, they all satisfy this equation. So we can obtain like K1 squared times S hat minus I matrix, unit matrix times E1 minus K0 squared epsilon tensor over epsilon 0 times E1 is 0. And the second solution also satisfies this equation, so we can write it in the same way. Okay, and now what we will do is minus these two. Use the first one to minus these two, the second one. So you will have K1 squared minus K2 squared times the following part. Okay, but as we have known that these two are different solutions, so we know that K1 is not equal to K2. But however, this equation should be 0, so it is not impossible to set this one to be 0 because these two are not equal to each other. So the only possible way to have this equation to be 0 is that all of this is 0. So we can then obtain the condition of the two solutions that E1 dot E2 minus S hat dot E1 times S hat dot E2 will be 0. Okay, so in the following slide, I will use this condition to prove the orthogonality of the eigenmodes. Let us back to the expression of the D field. For solution 1, we have D1 expressed in this way. And for solution 2, D2 can be expressed in the same way. Okay, then let's check what is the result for D1 dot D2. Okay, we take the expression of D1 and D2 into this operation, then you will have the result shown here. Okay, and clearly you see a very familiar solution which is placed in the previous slide here, tell you that this one is 0. So since this one is 0, we can know that D1 dot D2 will be 0 too. So we can have a conclusion that D1 is normal to D2. Okay, then we check another situation. That is, if we use D1 dot E2, we have D1 here, and D1 dot E2 can be obtained as and again, we have another 0 term here, so the result for D1 dot D2 is also 0, which tells us that the D1 is also normal to E2. Okay, then and clearly you can prove that D2 is normal to E1. So we can plot the relationship of this vector of these two more in space like this. We have a k vector here, okay, and along the k vector you will have the unit vector s hat. And then if you have the first solution E1, let me plot it in green. The first solution E1. Then in this plane, you will have the corresponding D1 for solution 1. Okay? Then by this condition, you know that D2 is normal to D1 and the D2 is normal to E1. So I have to plot a vector D2 which is normal to D1 and also normal to E1. So the D2 should be in this direction, which is normal to the plane in green. And we have D2 here, and clearly E2, D2 and K, they should be in the same plane. So the E2 should be in this direction. Okay? So D1, E1, K, they are in the green plane. D2, E2, K, they will form the brown plane shown here. And this is the orthogonality of the eigenmodes in an isotropic media. You have seen that D1 is normal to D2 and D1 is also normal to E2. Besides, D2 is normal to E1.